Hello, everyone. We are happy today that we have Professor Ravi Pandey. Professor Ravi Pandey comes to Dando from CAP Sprint program. This is a program to exchange research for different parts of the world. And Goofy has this program. Okay, we stay here until 18th of this month. Professor Ravi Pandey is a chair of physics in Michigan Tech in USA. Pandey received his education in Harrisburg University, Sagar National Physical Laboratory, Delhi, Atomic Energy Research Laboratory, Harwell, UK, and the University of Manitoba, Winnipeg, Canada. He has participated in multidisciplinary efforts, theoretical and experimental, to building programs in novel nanostructures, industrial and national laboratories. He's a fellow of American Physics Society and welcome to Dando and to Universidade Federal.
Thanks, Rodrigo. It's really good to be here. I come from north of the US, Michigan. So this is a beautiful summer for us up there, but it's a winter but sunny. So I'm really enjoying it. And for me, Rodrigo is like a 10-year meeting, reunion. He was with us in Michigan Tech. And partially I called him a guru because he taught us how to do electron transport calculation. And I believe he's really one of the most expert in the world in doing these calculations. So I start my talk, this including his work, 10 years ago he did. We set up the base. And the first time, Rodrigo's collaboration, we realized that interface is very, very important, especially when you're looking at nanomaterials. So I'll basically give some little brief introduction and then give a few examples. Like I said, I come from Michigan. This is a way up in north. You have the New York City here. Chicago is here. So we are closer to Chicago than sort of in New York City. But it's a beautiful area next to the Lake Superior, which is one of the largest freshwater lake on Earth. So I'll talk about simulation and theory, which I come from an experimental background back in India, but then I switched to simulation when computers were coming up. And the whole idea which we would like to sort of convey that what we can provide really fundamental understanding and the foundation of these interactions, which are really going to be important to look into the responses of the materials either electronic, optical, or mechanical. So what we are looking at is a structure property relationship employing these quantum mechanical or quantum chemical methods or atomistic methods. So in my group, there's one problem in US, in America, that you have to change your field every 7 years. Otherwise, you will not get the funding. So I use the same tool, but I started looking into the crystals, the clusters, nanostructures, 2D materials. And now the buzzword is we call biomolecular electronics. So what I believe, especially the young generation, the interaction of these materials with biological molecules has become very, very important. And please see if you can explore into that area. So I think we have to be really grateful or thankful to experimentalists. That's why we're here talking about the nanomaterials. And I was talking to the chemistry professor there. is without the characterization at the atomic level. We could not have made a lot of progress. The big contribution coming from these two sort of instruments is the atomic force microscopy, which gives a really high contrast and sort of provides the physical properties. And then we have SEM, which gives a high depth of field and basically tells us about the chemical composition at the atomic level. And this is one of the examples, say, of an image. Really, you can pinpoint the gold clusters of the nanometer size that is almost 20 years ago. So then, to extend tutorials, I have this slide which sort of spans what kind of tools available to us. So if you look at here is a time scale, this is a length scale. So if you're coming from down here, this is mostly related to engineering. We're looking at the permeability, mechanical response using a finite element analysis. If you come further down is a mesoscopic, then we have atomistic, and then we have quantum mechanics. So today I'll talk about basically this sort of a little area where we can deal with the angstrom to nanometer length scale in about femto picosecond time scale. And our aim is to look into sort of the structural, electronic, chemical, or mechanical properties. So this is a nice slide which sort of, I don't know if you can read it here. So these are the tools available compared to here the length scale versus the time scale. And coming from again down is the optical microscopy, looking at the different sort of the continuum models. And you come down is to high resolution TEM, where we have the merge with the quantum mechanical models. So you can see a synergy between experiment and theory at this level. This slide I like about, if you go and say graphite is a pencil, nowadays nobody uses it, but the old timers like me, we can see we have used it, and you start magnifying it, it's a 300 times. In an optical microscope, you can pinpoint the tip. You can further go down, this is the electron microscope, and it's about 90,000 times. And what you can see here is the surface structure. And further go down, and we are talking about now STM, and really you can sort of image these hexagons, the carbon hexagons coming out of this graphite material. So this is such a powerful technique we have nowadays. So I'll focus on interfaces, why they're important. We can first, if we look at the experimental part, we can image them. We can look into, so this is a 2D gallium nitride with the graphene heterostructure. If you look at the so-called this TM image, high resolution, you can see here, this is a substrate, silicon carbide. You have gallium nitride monolayer in this case, and then you have graphene coming out. So you really count number of atoms forming this interface. On the theoretical side, we have a really powerful tool based on quantum mechanical or quantum mechanical model. We can pinpoint, sort of look into the electron density of, say, a graphene or a biological molecule with carbon in a tube. And how does this electronic cloud density interact? So both sort of go hand to hand together in terms of precision and the details about the problem. So I'll pick up sort of one of the examples first, which with Rodrigo we looked into it, the graphene boron nitride monolayer, and then I'll sort of give a different flavor from electronic and electrical properties to look and see if we can do the mechanical response. And then I'll skip, if I have time I'll do it, otherwise I'll just pick up these two topics in this talk. This is the first slide, and I'm going to the last slide about the equations, and I have to show it. So what we use is this so-called this density function theory, and we have a real system, nuclei and electrons. And we make a Born-Oppenheimer approximation to arrive at so-called Kohn-Sham non-interacting system, where electron basically moving around in the fixed potential of nuclei. We have this Kohn-Sham equation, and the trick of the trade is is what we do is we calculate so-called the ground state energy, which is a unique function form of this electron density. So in our so-called the black box of this program, different programs are available. We are calculating the total in the system with respect to the electron density. And once we have the minimum, it takes time. Especially the students can take years to find this minimum. But once you have it, you can characterize the material very, very accurately. So graphene, you may have seen this slide before. We know is a beautiful material, and the reason being this ultra high electron mobility. And they have this so-called band structure that we call the Dirac cones, where these the conduction band, which is the unoccupied, and valence band they meet. And that's why it's what provides this very high electron mobility. But there is a problem. If you're all electrical engineer, you said this graphene is a useless material, no use. Because for a transistor, what they want to have a very, very small but finite gap. They don't want a zero gap material. So the early efforts came out how to induce this gap in this material. So this is as a zero gap material. Definitely cannot use the devices because for field effect transistors, we need a finite gap to modulate the current. So the idea is came out how to induce a tunable gap. So again, this is an experimental paper back in 2009. So what they said is, let's take the graphene bilayer and we apply the electric field. So you can see here, because the distance, the carbon atom in this the lower layer is going to experience a different electric field compared to the upper layer because they are separated. So this difference in electric field induces the inhomogeneity in the carbon atoms. This inhomogeneity basically gives you the gap. That's the physics behind it. So they made this device. This is again typical bottom gate. It's dielectric material. You apply layer graphene and top gate, apply the electric field. And what you can see here, this is the without the electric field. You have the zero gap, but once you apply the gate field, it sort of induces a gap. But again, go to the electrical engineer, they said is, yeah, concept-wise it's good, but it's not easy to make these devices when you further apply the gate field to reduce the gap, because there's an additional variable in the system. So we thought, let's do something else. So we looked into around and say is, can we make a heterostructure, bilayer, where we have the graphene, but we have the different material. If you look around, see, there is a material called boron nitride. So graphene and boron nitride are very, very similar, but there is a difference. The boron nitride is semi-ionic compound. The ionic bonding is different, chemical bonding. So, and it's also a semiconductor. So our expectation is, look at the boron nitride and graphene. This carbon sees boron, and the other carbon sees nitrogen. So this interaction with carbon boron, carbon nitrogen is going to give inhomogeneity in the electronic distribution of these carbon atoms, and you're going to have band gap. That's the hypothesis. So we did a lot of calculations. This is a slide for the people who do the modeling. This gives you an idea about the functional forms. So we have, as you know, we have LDA, GGA, and VDW. So this is a very, very approximate form. And you can see here, the binding of this bilayer system is almost invisible as you improve the accuracy. So you have to go really very, very high in the accurate sort of Hamiltonian, which improves so-called the van der Waals interaction. This sort of shows. So let's come back. So we did again is this calculation, graphene boron nitride monolayer, you optimize the distance, look at the total energy, and when you have the minimum energy, you say, I have the equilibrium configuration of the system. And once you have it, you do a lot of other post-processing tools to look at the band structure. So this is the energy, and this is the high symmetry points. So pick up the graphene, graphene. We have boron nitride monolayer. This is a boron nitride bilayer. This is our heterostructure graphene boron nitride. The reason we picked up boron nitride bilayer because it gives a reference point. Like an experiment, when we do any experiment, you have to have the reference point. So we are trying to mimic the similar situation here. For graphene, you can see here, this is zero gap. The boron nitride has a very large gap, which you expect. Boron nitride bilayer, again, is more or less large gaps for symmetry. And graphene boron nitride we see is some sort of similar behavior. So when the student showed me this first time, I said something is wrong. He said, let's zoom in, because the interaction is going to have very, very small gaps. So he zoomed in, and you can see it's about a milli electron volt opening of the gap. Now we had to do some experimentation to see if it's correct or not. So our hypothesis is if gap opening is due to this inhomogeneous charge distribution in the carbon lattice, because the interaction, what happens if I reduce the interlayer distance? It's going to have large overlap of these electrons. It's going to have a large opening of the band. This again is the experiment we always do it. And so you can see here, this is our equilibrium structure. Now we are applying the strain, so reducing the distance. So these ions or atoms are interacting more and more. That should open up the gap. And that comes out very nicely that as we reduce the interlayer interaction, the gap opens up. Now for the reference case, we do not expect to open it because the boron nitride bilayer. You can see it remains flat. So that sort of proves that indeed there is an interplanar interaction which induces inhomogeneity in the charge density of this carbon sublattice, which opens the band. So we had done this work. Our program manager said, so what? Where you can apply? Can you make a device out of this structure and look into it? And that's why Dr. Amorim showed up and he said, let's do some calculations. So this is again a well-known figure. So what we have done again is with Rodrigo's collaboration, we picked up the interface, the graphene, the monolayer, bilayer, or trilayer, and we applied this left contact, volt contact. And again, we are looking at the bias less than 1 volt, because you have to be very, very careful. We are applying this bias at a very, very short distance. So breakdown voltage of field is very, very high in that sense. And this is the technique we'll be using, a non-equilibrium Green's function, which if I can get this thing. So what it does, you've seen this, again, is coming from one of our earlier collaborators, Rosha, which Rodrigo worked with him. So we are looking at this sort of quantum region, and then we have the left and right contacts, and we have this so-called the contact functions, gamma L, gamma R, which includes their contributions. So from here we have transmission function, and from there we can derive so-called the current versus voltage characteristics. So you can see here from materials we have gone with device, and we can give this IV curve to experiment. You can see how good or how bad the material is. That's the connection with the industry or the experimental physicists. So we have, let's start with the monolayer. This thing. So we have either a graphene and boron nitride monolayer, single monolayer. We are in the context. Look at the current versus voltage. Now graphene is zero gap material. We expect it to be ohmic like conduction. Makes sense. Boron nitride is a semiconductor. Our expectation is going to be diode like have it sort of flat and then takes up. This is not the case here. It just behaves like a metal with the ohmic current. And then again, as an advisor, you said, ask the student, go back and do more calculation. Because again, it's not true. The physics tells you it's not correct. But he came back after 3 months of doing a lot of things. No, this is correct. This is the number I get. So again, we thought, let's look into it. What is going on? Okay, but before that, we moved on to so this is a monolayer system. So let's play with the 3-layer system. Let's increase the bit thing. See what happens there. So we looked into the left and right context. And instead of a monolayer, we have so-called the 3-layer system with a different combination. And what you do is you look at the graphene on top and bottom, and the boron nitride in between, or vice versa. Boron nitride on top and bottom, graphene in between. And we are looking at here the transmission function versus energy. The 0 is my Fermi. Okay. So with the 0 bias for this particular case, we find is the black is basically the graphene dominated system. You have a small peak, transmission occurs. This will be current. For boron nitride case, which is red, you can see is a flat, it's sort of showing is a gap with no transmission around Fermi. So at the 0 bias, these heterostructures behave like what we expect. Once we turn on the feed, you can see here, this is our applied window. We have finite transmission. It doesn't matter what the material is. It's going to be metal-like heterostructure. So in this sense, you can see either monolayer or a tri-layer material. They behave just simply like ohmic contacts. The ohmic current is coming out from those heterostructures. Although there is a gap in one case and there is a 0 gap in other case. So look at okay. So you go to chemistry and say look at the chemical bonding. What is going on? And that's why we talk about this interdisciplinary nature. Because in physics, you have solid state, you don't care about the bonding as such. But we are looking at the nanomaterials. And you can see here, the chemist friend told me, Ravi, boron is an electron-hungry atom. It loves electrons. You can see here, it shows up the gold boron contact. There's a large overlap related to gold carbon contacts. So you can see here there's a material, the boron or carbon, they love to form bond with gold. So the interface is sort of taking over the material's intrinsic property. That's coming out message. So what we have again is strong bonding at the interface, which provides the additional conduction channel. That's why we have ohmic-like or metal-like conduction. How can you prove it now? So we thought, let's do an experiment. So this is my configuration, and we know this bonding is strong. Can I weaken the bond? So there are two ways. You increase the distance between contact and your material, or you increase the thickness of the material. So interface effects are going to be less dominant. So you can see here, so we are again is looking at this graphene, and now we are varying the contact versus this monolayer separation. So this is what we have, 3.1 angstrom at the equilibrium spacing. I increased to 3.4 and the 4.0. This is the Fermi at 0. So you can see here, by weakening the effect, the transmission goes down, but graphene is a 0 wave material, so we have to have a finite transmission. It sort of makes sense. Let's see what happens to boron nitride. This is this, we started from here, finite transmission at 0, comes down, and you can see 4 angstrom, just behaves like a semiconductor. It's a very, very small transmission. Then we go to other spectrum. So this is simply we played around the contact material distance. What happens if we increase the thickness of the material? Yeah, monolayer, bilayer, trilayer. So it's going to reduce the interface effect. You can see here graphene is a monolayer. This is the bilayer and trilayer. You have the Fermi. Transmission goes down but remains finite. The boron nitride case, monolayer, bilayer, and trilayer just behaves like a cylinder. I know if you remember this curve. So the message comes out to you is for nanomaterials, you can do whatever you would like to do, predict the calculation, do something. But when you make a device out of it, we have to be careful about the interface effects. And we have to have a thick material if you really want to make these devices in this sense. And there's a experimental paper coming from our Michigan Tech Group labs. This is a boron nitride. And you can see here in the monolayer case, like a metal-like conduction. But it goes to 7-layer boron nitride, it has diode-like behavior. What you guys see? What happened? Did I do? So I switch the gear now, and let's look at the sort of electronic, the mechanical response of the material. Can we get some kind of guidance to experimentalists by doing these calculations for a macroscopic scale coming from the quantum mechanical scale? So pick up an example with the polymer graphene composites. So Michigan Tech has got this grant from NASA to look into so-called the ultra-strong composites. And their aim is, NASA's aim is basically look into this so-called the deep space exploration or the next generation the rockets and ships. So they're looking at this carbon nanotube based sort of lightweight aerospace structural material. So let's look at the basics again is the chemistry, which I do understand. Typically, polymer composite comes in the so-called matrix and reinforcement. So you can see here, this is the matrix, and then you have the reinforcing phase, which tends to be a fiber. And this fiber and the matrix they form an interface where the action is. So let's look at this here. This is the way they prepare the sort of sample. It's a natural graphite. Yeah, of course, the surface modification, the functionalization, mixed with the matrix, sort of shake it, and then we have so-called the nanocomposites. So the definition which we need to be careful about is how do we define? So we call the material is to be sort of, you can see here, the tough composites where the interface between this fiber and matrix is very, very weak. So when you sort of apply the external pressure, it sort of breaks. Like that. Then we have the strong interface where we have the little elastic deformation as we apply the pressure or external field. So we have weak interface and a strong interface, and that's what we have to figure out. Are we looking for a so-called higher fracture toughness or low fracture toughness? The toughness is the criteria a mechanical engineer looks for. How tough the material is. So we start again some approximations. So they experimentally use so-called the flattened carbon nanotubes. These are very, very large diameter carbon nanotubes. So they have a nice sort of surface. So instead of taking this as our model, we simply go to graphic surface. graphene. And then we have, again, I don't remember still all the acronyms, but this so-called biphenols A diglycide ether. So I use this sort of acronym BGEPA. This is a simple monomer, not a polymer, monomer. You can see here it is sort of carbon rings, there are hydrogens, and red are oxygens. And then you have this periodic supercell model where our composite is simply a graphene interacting with these monomers. And that's again is I call ground zero. Very, very approximate model before you move to a very complicated model. And then what you do is take these molecules and do a different orientation to get the total energy. So we have so-called this flip-up configuration, flipping a vertical and in plane. Coming from physics and chemistry knowledge, we understand this configuration is going to be more stable. And the reason being is we have larger number of atoms interacting with each other by so-called the pi electronic cloud. Calculate so-called the interaction energy versus these configurations, which is nothing but the energy of the system minus we have graphene and a monomer. And you can see here the in plane configuration is considerably more stable for this case. And then you have again a lot of different molecules. This is epoxy. This is so-called BMI. And this is called aeroside F10. So in a polymer, you have a so-called resin and you have a hardener. And you mix resin and hardener together. So the first three sort of cause resin molecules or monomers, and these are hardeners, DETDA and DABPA. And the reason the difference here blue is nitrogen. They have some nitrogen atoms. So you do all these calculations, find what the interaction energy is. And this work takes about a year. You can see it's not easy. And once you have it, the student sort of gives you a plot. So you have these different resins and hardener, and you have some idea about their interaction energy. So again, so you talk to engineer, and they say, yeah, that's fine, it's a fundamental science. But can you guide me? What is going on in terms of the mechanical response? So okay, look into it. So this is so what kind of experiment do they do? So simply they have on experiments to look at the strength of the material by pull-out experiment. So you have this polymer matrix, fiber, and simply pull it out. Very easy experiment. So what they're doing here, this is strain, they are applying. This is the stress, and this is so-called initial stage of debonding, and they're pulling it out, and at one point, it sort of it breaks. So that's what we have, the debonded, and then sort of it goes down. It's completely collapsed. So the key thing is, what they would like to know, what is this critical point that determines if material is a tough or not. So yeah, we can do it. We to simply do the simulation. So we have a monomer surface, simply pull it out. So what you have, you're generating the energy versus distance. Once you have energy versus distance, you can calculate the force. Force versus distance. And then you have stress. And then simply you look around, because you have to again do a lot of approximation. We are talking about not the bulk material, but is I call quasi 2D material. So you use the so-called this equation of state to fit force versus your strain to look into this behavior, stress versus strain. And from there, you can have so-called the bulk modulus, or Young's modulus, shear modulus, or other elastic properties. So we do it. So as I said, we have energy versus distance, from where we get force versus strain relationship. And you can see here, we have the different curves. This is the resin molecules, and this is the hardener. And more or less they are same, but except the one case, which is the green called DPCA, sort of stands out. It goes further about 12% strain than the other molecules. So we said, okay, we have all these things. Can we guide experiments? We thought, okay, let's make it this so-called the diagram. And the one student made this diagram. I said, this is your PhD. Because this sort of sums up all the results after 4 years. So she has done, it's called interaction energy, you have strain, and you have the stress. And you can see more or less these sort of in the same sort of criteria, but this sort of stands out compared to this or sort of this. So all these things can have different molecules, and what's coming out is from this result that the nature, you can see they are different. They are more the same molecules, but a single oxygen, single nitrogen, or two oxygens, they have a subtle difference in the interaction. That induces a different response. So nature of interaction does play a role, and then we talk about which one is better than the other molecules. So when we showed this result to engineers, they said, well, this is only graphene, this is a monomer. It does not represent the real polymer. The polymer, you have a number of molecules interacting with each other. Okay, let's move one step up. So we move to so-called the atomistic force calculations, the molecular dynamics calculation. And looking at now, not few hundred atoms, but about 45,000 atoms. So we have the knowledge of this quantum mechanical interaction potential, the force field, and we feed it to now our engine model. So this is sort of a scale-up process where we can look into the large number of atoms. So this is again a sort of step function. So we model the monomer, which we had done it. Then we generate so-called the graphene in the supercell. Then this is combined. So you can see here you're forming a polymer interacting with so-called the graphene or carbon nanotube, large diameter. Then you sort of apply the temperature, mix it, anneal in equilibrium. So we have gone up to 700K here in different sort of ensembles, and then we equilibrated NVT about 300K. Once you have it, then you so-called this polymerization step. And then the experiment. So you have this polymerized structure on NV's model, and now you start pulling it out. Pull out experiment. And this again you can see is a very easy step, but it took about a year to complete this step. So they are very, very expensive calculations. You see the results. I picked up. Now it's just a case, it's changing things from graphene vapor boron nitride, the epoxy, and the BMI molecules, the polymer, sorry. You can see here, this is epoxy, and we start pulling it out in time. Oh, is the animation not coming up? That was the best part. So you can see here, of course, it's not showing up. Can you see if it works? Animation.
I think because it's Google.
Oh, it's a Google, okay. If you give me a minute.
Can show the cable here.
It's okay. For this page, which is a 10 order page. Sure, right now. Today I want to look at the difference, which is nice. So the first case you can see is doesn't matter how far you pull out, more or less remains the same. Okay. The second case, I will repeat again. First case. Second case, you can see very nice. You can see this is again is a polymer compound, epoxy BMI. The difference in BMI has few more oxygens. So it's a game of again chemistry. It's intermolecular bonding versus intramolecular. So the BMI prefers the binding with the graphene. It doesn't care about the BMI molecule, so it sort of splits apart. Epoxy, they love each other. They don't want to get away, so they say, okay, fine, we're going to stick together. So it sort of reflects in there. You can see here the red is epoxy, and BMI is sort of smooth, slowly sort of breaks apart. But epoxy, they love each other. So you apply the strain, they break. So very, very strong compared to the weaker intramolecular bonding. And you can have this number, you can see the distinctly different. The toughness, the epoxy in this case is about 37 millijoule per meter square, and BMI is 98. So what's coming out is these are the so-called quantum mechanical or atomistic calculations. And what we're trying to do is look at the mechanical response of the material. And simply, it sort of like becomes a guidance to experimenters. Because they have 100 different polymer molecules to choose from. Which one they focus on. So given the choice, if you have epoxy or BMI, I'm suggesting them to look into the BMI. Which makes life easier for experimenters. Because this is a guidance. So, how much time do I have? Okay, so I'll open the question. So again, I'll skip let me have one slide. This is a very interesting material coming out. Is we have electronic properties, mechanical properties. What about the optical properties? Because as you know, there's a push for optoelectronic devices. Most devices are silicon. Silicon has an indirect gap material. You cannot use silicon for optical devices. So what you do, you have a chip, electrical device and optical device. So they want to merge in the same place, optoelectronics. So graphene is a centrosymmetric material. So what we have is so-called this the second harmonic generation, which is non-linear optical property. It cannot have it. It's like a zero gap material. It's happy as it is now. So idea is how to perturb it. And we want to use graphene because of in-plane high electron mobility. So what we said, let's bring in like any other material, 2D material, like a boron nitride and the phosphorine. Now we picked up these two because boron nitride is a planar. And as you know, phosphorine is of phosphorus atoms. There are a lot of electrons. And it's sort of a buckled structure. So it can provide a little higher dipole moment to graphene compared to boron nitride. And you can look into the differences. So what I want you to, let me see. Yeah. So we calculate this so-called, again it's coming from the microscopic to macroscopic properties. And this is, I think, for the young generation, I would like to think about the big picture. That we have this energy can be derived in stress-strain relationship. If I have the so-called the beta value, which is second order hypercorrosivity, how can it connect to the experiment, which is macroscopic? The information is out there because this is all approximate. So here we picked up the quantum mechanically derived beta applying to the volume. So you get a sort of a macroscopic, which relates to called second harmonic generation, which experiment can measure. You can see here this is the case with the phosphorine. This is the case with boron nitride. Because of this sort of electron-rich phosphorus atom, it provides a larger perturbation in graphene pi electron cloud, and that's why it gives a very, very high SHG value. And this again, like I said, is a graphene boron nitride, you can see, but this is this phosphorine. It provides a higher degree of anisotropy, which makes this heterostructure to be NLO. That's again so. So if we go back, thanks a lot of people. Over the years, I've been around for a long time. So a lot of students, postdocs, and a lot of colleagues have been around almost 30 years. And the best part is, which I tell, I did my PhD from Manitoba. I'm looking at the electron trapped in an oxygen vacancy in NGO. We wrote a 50,000 line code in 5 years. I'm not going to go back in late 80s. We are not born. And when I calculated the quantity, I got the sign right, not the magnitude. And my advisor said, this is your PhD. In 30 years, look at the progress. You can calculate the same thing within the 1% of the accuracy in 10 minutes. So I call is, your generation is really lucky enough to have such powerful resources. Please use them. That's the message coming out. Of course, Rodrigo is a good colleague and a good host, but I have to special thank Deborah for a wonderful host. So thanks again. I'm open to any questions.
Questions, comments?
First of all, I would wish to thank the Professor Karim for that very friendly presentation. I'm not even from the area and I understand much of it, not so well. But I have some questions. But the first one is, why have you worked with boron nitrogen? Could not work with another element?
Agree, but the reason is the similarity. Because whenever you make a heterostructure, you have to worry about the lattice mismatch, which induces the strain. Can you show me the on the slide? Okay, see here, okay. So lattice strain is about within 1%. So if you form a heterostructure, if suppose I take a phosphorine, it's a large lattice constant. So they're going to match and it's going to use the strain in the heterostructure, which makes it unstable. So structural similarity, but the other good thing is this is semiconductor, this is uniconductor. So the bonding also does matter because our expectation is the interaction is going to have a different electron density in this covenant, which opens up.
and that they are the only one that have that kind of property, right?
So you can have other things, but these are the lattice matched heterostructures. So for experiment, they prefer the lattice matched. They don't want any strain. They will change the properties.
Thanks.
Question?
At the beginning, every time that you create a homogeneous charge distribution in the system, you need to create a band gap instead of
That's like a rule
every time.
in graphene. Because this came out from the experiment. That's the whole idea was. So the graphene bilayer, they apply the field. This one experiences a different field than this one. So they have different degree of perturbation. Because ultimately, the bands come from the overlap of electron density. If they are the same, they like each other. If they are slightly different, they start disliking each other. That's a gap.
Excuse me, Professor. Thank you for the presentation. I have some questions. The first one is about you told the first line of the presentation that there was a minimum, a difficulty to find the minimum of electrons.
Yes.
That's what is this difficulty? Because last
So the difficulty is, which I have not shown, so we are solving the Hamiltonian. Okay, so we have to have this so-called the wave function, but the density is not electronic density. Okay. So we start with our Hamiltonian, but you have to have a guess. How do I start? So we say, let's pick up the atoms, which are far apart. So you take the density, you calculate the energy. Now you have to call self-consistent loop, iterative loop. So you modify the density, then look at the new density. And if the difference between these densities are very, very small, then say, aha, I had it. That's the one part. And then you have to optimize this nuclei to get the density. So the first part is very difficult. And you can ask Dr. Amorim's students.
And the second part you said about talking about the dynamic structure of the field, and really remind me the diagram of information tension. Have you ever heard about it? You do with carbon, iron. Tension deformation diagram. It's well known in engineering, and it's pretty reminding me. And I don't know if it would be truly successful, but I think it might be useful to think in graphene. When you told about thickness, this diagram tells about it as the extraction limits, as the plastic area, the elastic area.
The mechanical properties.
Yeah, about that. And but it did with graphene, so
Yeah.
it really remind me. I don't know if that is the way you are seeing.
In a sense, you're right, because we are looking at the polymers is nothing but carbon atoms with the graphene. So you can go back and look at the pure pristine graphene, which I think we have done some experiments, calculations, to look at the young models.
Yeah.
Somehow you say it's like an analogy.
Yeah.
Other questions, comments?
Before this thing, if you're coming from engineering,
No,
okay, so what happens in engineering, the pull-out experiments is very easy.
yeah.
So what they do is, they do called nano indentation. I can show you some results. So they use the tip and then press it.
Yeah.
You get the what time it breaks.
Yeah, vertical force and all
Yes, sir.
Thank you, Professor. It was impressive beginning the second amount generation with the faith. It's just one layer. You can control it too.
So what happened? I'm happy to ask the question because this is the recent results, and we're not expecting. So, can you go to the last slide? Last. Just last one. Yes, for this. Can you pull up? Yeah. So you can see here, what we are looking at is an anisotropy in the heterostructure. Okay. So you ask is, what happens if we increase it? Change the distance experiment. And you can see here, I didn't go through it. So this is, the black is 3 angstrom, and the blue is, sorry, should be the other way around. This is 3 angstrom, this is 3.4, yeah, so reduce it. So you can see here, this is my equilibrium increases. So indeed this comes out to be true that anisotropy is responsible. So graphene as such is useless. You bring in a material which is the higher degree of inhomogeneity electronics.
You have the use of such structure for clean photon generation, for example.
That's a very good question, and if you give me one day, tomorrow I can talk to you about the gold doped with rare earths. We are looking at the 2 photon. You're right, but that's the next step. Next step. And that's very exciting. Calculations are not easy. The 2 photon absorption is called the buzzword.
I think thin film and thin crystal approximation is very good for this.
Agreed. And that's what we did. If you can see, this is approximation here, just to get an idea. Because for you is beta value doesn't mean anything. You need SHG. And that's the connection I think students should worry about. What we calculate and what they see and what they observe. We have to have some kind of connection.
Any other questions? Let's thank you, Professor again. Professor, we stay till tomorrow here, and if you want to talk with me, just let me know. Okay? Thank you very much.